So, fundamental theorem of calculus part 1. Well, I introduced part 2 to you the other day. It's not uncommon for teachers to do that. Part 2 is probably what we apply more. Again, that really focuses on the area part. It also focuses on finding an antiderivative. Remember that big F is any antiderivative of F. But the fundamental theorem of calculus part 1, and I'm going to write it kind of a shorthand for it, but it talks about the area function. So it says that g of x is your area function. It's an accumulator. It collects stuff, like a garbage truck, okay? I know how much it collected. Well, the function is equal to the area function from a to x of f of t dt. This looks like that, right? So we're calling it a function. If you take the derivative of g, anybody want to guess what you get? Very close. F of x. You get the function, the original function. Yep, we wrote it once before. We're writing it now so you can see them both side by side. So I want you to understand that there are two parts of the fundamental theorem of calculus. Yep. It's my next reading. I'm going to read over some of the history of calculus, so I can know like when part 1 came in and when part 2 came in, all the different things. So anyway, see if any of you want to read it with me. You can have a book club. Okay. Graphical representation of fundamental theorem of calculus part 1. We have a function. We will call it f of t. And we're going to bound that function from a to x. As we talk about this area piece is g of x, which is the integral from a to x of f of t dt. Is any of this surprising to you so far, the way I wrote this? That's the area function, so I set it in the middle of the area. So let's think about what Kyle said. I asked, what is the derivative of that area function? And it is a function. As I move x closer to a, what's going to happen to the area? It's going to get smaller. As I move it to the right, it's going to get bigger. Obviously, that depends on the function, but for the function I've drawn, that it would seem that that'll be reasonable, okay? So depending on where x is, the function value changes. If you take the derivative of this, you get that thing that sits right on top. So the derivative of the area function is f of x, or the function that serves as the boundary. I'm going to try one more time to connect this together for you. This is the graph of f prime of x. Can you tell me, is f of x increasing or decreasing? Why is it increasing? The derivative is positive or negative? The derivative is positive. This is the derivative, right? It sits above the x-axis. This is positive. So therefore, f of x is increasing. F prime of x is the derivative of f of x, right? So f of x is the antiderivative, correct? F of x is like the area function. Well, look at this. This is a derivative of the area function. Is this positive or negative? Because it sits above the x-axis. So is the area increasing or decreasing? Increasing as we move to the right. Exactly. So that's what we're trying to bring to you. Let's try some numbers and plug them in and see what happens. Let's attach a function value, f or g of x is equal to negative 6 to x, the integral from negative 6 to x of f of t dt. It wants us to evaluate g of negative 6. So what that means is g of x is equal to then the integral from negative 6 to negative 6 of f of t dt. And we will call this right here your f of t. So that's your function. So I'm going to go back to negative 6. 1, 2, 3, 4, 5, 6. And I want to know the area because integral represents area. What is the area from negative 6 to negative 6? 0. There is no area because there is 0 width. Right. We will fix negative 6 as the starting point, and then we will move from there. Now, remember, f of t is the derivative of the area function. Is the derivative above or below the x-axis? So therefore, the area should be increasing, correct? In fact, what is the value of f of negative 6? 1. So therefore, the area should increase at a rate of 1. As I move 1 unit to the right, how much area do we pick up? 1. Okay. This is the derivative of the area function. Let's do negative 4. I moved to negative 4. What's the area there? 2. We picked up 2 units. Is anybody surprised by that? Nope. Uh-oh. What happens with the next spot? Very good. We collect some area, but we also lose some area. We have this portion, which is positive, and it looks like that will cancel out with this portion, which is negative, correct? But we also gained this extra piece right here. So what is our total accumulation thus far? We gained 1, 2, 3, and those canceled out. So we have a total accumulation of 3. As I continue to move on, I'm going to move to 0. Am I gathering area or losing area? I'm losing area. And what do you notice about the derivative? The derivative sits below the x-axis. So therefore, that tells us that the area function would be decreasing. I would be losing values. Okay, approximately how much do I lose from negative 2 to 0? Yeah, I would say 5 is a really good estimate. So I lose 5. So what's my total area accumulation now? Negative 2. Now I'll move over to 2. Am I losing area or gaining area? I continue to lose it. So how much have I lost now? Lost 6 more, so a total of negative 8. Then I'll go over to 4. And again, the picture isn't exact, but it looks like I do have some negative area there. That will cancel out with some positive area there as well. But overall, would you agree that it looks like I lose about 2 more units of area? Okay. So that'll bring me to about negative 10. And then as I go from 4 to 6, am I losing area or gaining area? Gaining area. And what do you notice about the function? It is the derivative, and it sits above the x-axis. So again, when derivatives are positive, we are increasing. So you're gaining area. All right, about how much do I gain? Yeah, sure, I'd say 6 is a really good estimate. So that'll bring me to negative 4. All right. The question is, on what intervals is g of x increasing? Okay. Well, that's wherever its derivative is positive. What is the derivative of g of x? F of t is its derivative. We know that g of x is increasing wherever the derivative is positive. This function is positive where it's above the x-axis. So So would you agree that over those intervals, it would be increasing then? Very good. So, looks like I have from negative 6 to about negative 2.5 union with 3.5 to 6. And that would be your increasing. It would be decreasing from negative 2.5 to 3.5. Where does it have a minimum value? We'll say that we want parentheses. Brackets we won't use because technically at negative 2.5, it's neither increasing nor decreasing. It's steady at 0. Good question. At negative 6, you're right. It would be increasing from the beginning. Yes. All right. So if I have this graph, and I draw something like this, so this is my derivative. And I'm curious, where does the original function, f of x, have a min or a max? A minimum occurs when the function changes from what to what? Decreasing to increasing, correct? That's where minimum occurs, where it changes from decreasing to increasing. Let's not think about that. Let's just think about the picture. This would be a minimum, right? So I change from decreasing to increasing. So that means the derivative changes from negative to positive. Well, this is the derivative. At what point does the derivative change from negative to positive? At 0. Everybody agreed? So at 0, it has a minimum. Where does it have a maximum? A maximum would be where it changes from positive to negative. Where does it change from positive to negative? Negative 3 and 2, right? Agreed? So let's apply that same piece. So I brought it back to something we've learned before so we can understand this point right now. The question is, where does g of x have a minimum? Where its derivative changes from negative to positive. What's its derivative? F of t. Yeah, it changes from negative to positive at 3.5. And then it says to sketch a rough graph of g of x. So I'm going to do that with a black pen. And g of x has these values. So I'm going to use them to sketch a rough graph. At negative 6, I have a value of 0. At negative 4, I have a value of 2. At 3, I have a value, or at negative 2, I have a value of 3. 0, I have a value of negative 2. 2, I have a value of negative 8. 4, I have a value of negative 10. 6, I have a value of negative 4. So, it's a rough graph, but that's what the antiderivative looks like. That's what the area function looks like when we actually draw it as a function. Okay, so that's the big conceptual piece. I don't pretend that that's just easy to understand right away. Might need to go back and watch a video and think that through. But we're going to move to a second piece right now, and I want to draw your attention back to the fundamental term of calculus part 1. And this is probably what will resonate with you more. We're going to do a little bit of algebra. Notice that I asked what is g prime of x, and Kyle said f of x. Well, if I take, don't draw this, but if I take the derivative of g of x, or g prime, that would mean I would have to take the derivative here. It looks like I end up with f of x is the same as this. So how do I go from this to this? What goes away? What are some things that just disappeared? That goes away. That integral sign goes away, right? And that drops down into place. Okay? That's what we'll pick up with when we get back. Should be about 8 minutes when we get back of time, and then you guys will have time to work. Okay, so we talked about what disappears when you take that derivative. So I moved to this page. Let's drive through these problems. What we want to do is we want to use the fundamental theorem of calculus part 1 to take derivatives of these area functions, or derivatives of the integrals. And here we go. We're going to change this letter. Instead of t, it's x. So we want to take the derivative of g. We get, remember what happens. The integral symbol goes away. The dt goes away. And you get square root of, you plug in the x plus 3. That's it. That's it, yep. Wow. Who says yeah? All right, so this one, g prime of x. I take the derivative, and you can see that the integral goes away. The dt goes away. Now instead of just plugging x in for t here, you plug in x also here. We get 3x squared secant of x. Later, Gator. So, a lot of people in this situation, they would want to, okay, thank you for asking, okay? The question is, what's the point? 1.5 times 2. No, because nobody understands it. These are inverse operations, aren't they? Right? What's the inverse operation of sine of x? Anybody know? Sine inverse. If you take sine inverse of sine of x, you get x. You know what the inverse operation of e to the x is? Natural log of e to the x, and you will get x. So there's all sorts of inverse operations, right? Well, here's the deal. You know what the inverse operation of a derivative is? An integral. So those cancel each other out. It's the inverse operation piece. So that's what should kind of connect here and make sense. Otherwise, it just looks like we're doing sheer magic, doesn't it? Okay, what do you notice that's different about this one? The x is on the bottom. This is something important you need to know. If you have the integral from a to b of f of x dx, it is equal to the integral from b to a of f of x dx, except it is negative. So you simply just, if you reverse the bounds, you simply just make it negative. So we will do this. No, trust me, you'll remember. So I see the bounds, they're switched. So I'm going to rewrite it like this. It equals negative integral of 6 to the x sine of t squared. So I want to take the derivative of that. What am I left with? Yep. Here, again, we're going to rewrite it. It's equal to negative integral from 3 to x of natural log of t dt. What am I left with? Negative natural log of x. Now, can you anticipate what the mistake is that a lot of people make on the test here? Okay, that's one. Obviously, nobody's been tempted to do it. Was anybody tempted to take the derivative of this using the product rule? A lot of people will do that on a test. They'll say, okay, now I have to take the derivative of that. Or the derivative of natural log of x is 1 over x. When we took the derivative, it got rid of the integral and the dt because those are inverse operations. They undo each other. Okay? Okay, what's different about these last two? Yeah, it's a function that's sitting here. So as you look at this, I'm going to have to now set up the chain rule. So we have the integral from 1 to u of t over t squared minus 1 dt. What's the inside portion? What substitutes for u? 2x cubed. So what is it that when I take this derivative, okay, what am I left with? Except I write u over u squared plus minus 1. Remember, that gets plugged in. the derivative of 2x to the third? 6x squared. Remember when we used to practice problems just like that? All right, so we put that in there, 2x to the third over 2x to the third quantity squared minus 1. Multiply that by 6x squared. And I get 12x to the fifth over 4x to the sixth minus 1. What? What were you thinking? All right. So, what I gotta switch the bounds, right? And when I do it, we'll simply just get rid of that negative, won't it? Sweet, huh? I take the derivative. I have to use the chain rule. I have the integral from 2 to u of the cubed root of sine of t dt. You put it in for whatever the function is. I made it positive because I switched the bounds. Ask your question specific, please. Yeah, I need the 2 on the bottom. I need the variable on the top. So in order to do that, you make it opposite in value. Okay, so what is u? 1 minus 4x. That's going to be substituted in derivative of 1 minus 4x. Negative 4. I take the derivative of the integral from 2 to u of the cubed root of sine of t. What do you get? Cubed root of sine of u. So I plug that in for u. I get negative 4 times the cubed root of sine of 1 minus 4x. See what you said, Haley. Nice and loud. Okay. Got it. Excellent. It's a great point. And the reason why it just simply sits around is we're not just talking about sine. We're talking about the area function. And so when we take the derivative, we don't deal with this. We just get rid of the area portion. Okay? So those are the inverse operations. And that's what we try to get rid of. So I don't pretend that makes it easier, but continue to bring those questions up over the next few days as we talk about this. But conceptually, this is a tough thing to understand. Fundamental Theorem of Calculus Part 2, easy to understand than Fundamental Theorem of Calculus Part 1 for most people. Here you go. Book assignment. I know that you guys love to have worksheets, but a couple of your teachers reminded me in the past few days that they don't like seeing those worksheets in class. Like any teacher that I would tell students, I said, please put your whatever away so that you can focus on yada yada. I wouldn't say complain, no. I just sometimes hear from students, oh, we see a lot of math work happening in our classes. But I hear that cross-curricular. I hear that in science. I hear it in English. I hear it everywhere. So I would ask that you be respectful and to do your... That's great. That's fine. Do it at the appropriate time.